Really hard.
Really hard, huh? So I just wanted to say a couple of things there. First, I'm really proud of you for struggling with it. Frankly, I wanted you to experience sort of what it is to have data and sort of be confused and wrestle with it. I believe many of you were able to work through the first part, but when you got to a question where I asked you to assume that beta hydride elimination was rate limiting, it was more difficult. And basically there, even if you're not able to come to an answer, just show me your work. I want to be able to see if you're thinking about it maybe in the right way. I'm not, so be less concerned about, do I have the right answer than is my process reasonable? And clearly if I can't do something on paper, I can't penalize you for doing it. Sometimes in grad school, we try to push you a little bit beyond what should be reasonable and see what you do. But again, this is not going to be graded like an undergrad OChem exam where I'm looking for points to take off. Instead, I'm just going to evaluate your answers and the understanding you demonstrate. So any questions any of you want to ask?
Yes, I do so many options. So I just put one for you. Do you want to copy all the options that I do?
You can send me whatever you want. So, and if you've already sent me something and you want to send me a little bit more, that's fine too, whatever.
Yeah, on a similar note, I feel like if I explain all of my thinking, it'll end up being paragraphs and paragraphs of writing, which I know no one likes to grade. So I'm wondering.
Well, most of the, you should, in the ones where you're trying to think about rate laws, math is enough. Maybe a brief statement about what assumptions you've made. In the other cases, I think in probably less than 2 sentences, you can probably say, you know, this data shows that the reaction is 14th order in this reagent or whatever, right?
Cool. Okay.
Yep. All right. What else?
This to you on Learning Suite or email it to you?
You can email it to me. That's fine.
For question 4, you said derived in item C. Is that just question 2?
Oh yeah, I'm sorry about that. I thought you may not like this. I was going to write a second question. And so I had this, the first one was question 1. And then every sub item was A, B, C. So yeah, when it says question 4, derived in item, yeah, that would be whatever item you derived the rate law for.
I just wanted to make sure.
Yeah, that should be the for question 2, right? That's where the one where you wrote the rate law. Yeah. Okay. Yeah. Anything else?
For my own personal sanity, the test is due tonight at midnight, right? Or like right before midnight?
Yeah.
Okay.
It is. Though, yeah. So but don't stay up that late. It's not worth it.
Well, no. I just wanted to make sure because I don't know the way, I don't know. Just thought it was due today for some reason. And I was like, wait, no, I'm not done yet.
Yeah, it is, but by the end of the day.
Okay, thanks.
Okay, anything else? All right. So I believe we're not going to get to chapter 11. So sad for us, but that's okay. The point of this class is not to cover everything, but to show you how the principles we've learned of physical organic chemistry can be applied to learning about reactions and processes. So I think the rest of our time together, I guess we only have this one and then 2 lectures next week. Or is it just one? I think we have a Wednesday class, right? Yeah. Will be a survey of various reactions and what the kinetic data tell us about them. And we'll sort of jump around from there. We are going to spend a little bit of time applying our understanding of potential energy surfaces to understanding E1, E2, and E1CB reactions. We've been talking about addition reactions to alkenes. One of the more useful of these is the epoxidation reaction. The reagent that's typically used for this kind of thing is a per acid. A per acid looks like this. It's got a weaker oxygen-oxygen bond. The typical per acid is MCPBA. You probably remember having to try to remember what the heck that was in undergrad organic chemistry, but just metachloroperbenzoic acid. There have been some interesting kinetic studies that have sort of demonstrated what the transition state is like for this reaction. So I'm going to draw a transition state for an alkene. And actually, I'm going to put a benzene ring here, proton here, proton there, everywhere a proton. And in the transition state, the terminal oxygen of the epoxide, I'm going to just draw the atoms first. The terminal atom of the epoxide is in the process of forming bonds with both carbons of the alkene. There is a bit of a buildup of partial positive charge on the more substituted carbon where it's more stable. And if I can fill in the dots, at the same time as you're forming those bonds, you're breaking those ones. And what I've drawn here probably is terrible. So what I will do is do an arrow pushing mechanism so that you can see sort of what's going on in this reaction. So you can think of it as pi electrons from the alkene attack the terminal oxygen at the same time as lone pairs on that oxygen attack the other carbon. At the same time, we're breaking the oxygen-oxygen bond, and we have to break this pi bond, and we remove the proton from the acid. And so all of that's going on in the same concerted step. Some people call this a butterfly mechanism because—
Hey Josh,
yes.
Quick question.
Yeah.
I know a few class periods ago you talked about how it's better to draw the double bond going up to the oxygen and the high energy lone pair attacking the hydrogen. Is the reason they don't do that in this is because it'd be way too many arrows?
Oh, you know what? They probably do that in the text. I'm just continuing the false traditions of my fathers or whatever. I don't know. I honestly, it doesn't matter. Like Isabella pointed out last time, there's no way you could actually tell. But it makes more conceptual sense, I suppose, for the pi electrons to come up on the oxygen and then for this lone pair to do the attacking. So yeah, that's right. What I drew at first would have been acceptable too. So the transition state I'm showing you on the left involves all of those bonds breaking and or rearranging at the same time. One of the ways that we know this is through kinetic isotope studies. So kinetic isotope studies on the acid proton of the per acid give you a small primary kinetic isotope effect. KH over KD is around 1.2. And that tells you that proton transfer is involved, but is likely either complete or only partially done, but not sort of halfway through in the transition state. For the alkene protons, you see a very small but measurable secondary kinetic isotope effect, inverse secondary kinetic isotope effect. On this carbon, it's almost negligible. I don't really have a good feeling for what's significant in isotope effects because I've never done these experiments myself. And then on this carbon, it's 0.82. That's consistent with more rehybridization and more sp3 character at this less substituted carbon in the transition state than at this more substituted carbon in the transition state. That makes sense from a certain point of view because the more substituted carbon should be better able to support the buildup of partial positive charge in the transition state, assisted by the presence of this resonance stabilizer of cations. And then finally, the Hammett studies were done putting a, let's see, I may get this wrong. It may have been meta substituents. Let me just check. No, they were para substituents for this styrene kind of alkene. And they found that rho was equal to minus 1.1, which, remember, positive rho in a Hammett study was for stabilizing a negative charge. So negative rho is for stabilizing a positive charge. And this does support a small amount, not a full charge, but a small amount of partial positive charge in the transition state. So those are the experiments that sort of give you the picture for what's going on here. Your text, anything we need to say in addition about epoxidation?
In the transition state, would there also be a dotted line above where the double bond used to be, or is there?
Oh, Isabella, thank you. I'm so sorry about that. Yes, there should definitely be a line where the double bond used to be. Perfect. Okay, good. What else? Because the reaction's concerted, it should be stereospecific. That means alkene geometry is reflected in the epoxide products. There's no alkene geometry here for this styrene derivative that I'm showing you in the transition state, so there's nothing really to talk about. Your text does talk in some nice detail about some asymmetric epoxidation reactions, the most famous and useful of which are the Sharpless asymmetric epoxidation and the Jacobson asymmetric epoxidation. That may be worth looking at if you're going to do a lot of synthetic chemistry. I have it in my notes and I've drawn it all out, but I don't think it's worth drawing out here when you can just read about it if you're interested. Okay. So I want to talk now about, we've talked about addition to alkenes. We now want to talk about addition to carbonyls. And the first thing we're going to talk about is some interesting work by Hans Beat Burgi and Jack Dunitz at the ETH or ETH in Zurich, Switzerland. And they were crystallographers and they looked at the crystal structures of compounds in which there were carbonyls like aldehydes or ketones, and then potential nucleophiles in the same molecule. I don't know why they necessarily got into this, but that was sort of what they were studying. And they made a really interesting observation. So I'm going to share my screen with you. I'm already sharing my screen with you. I'm going to temporarily shift to a different window. And I'm going to share again. There it is. This is the crystal structure of the molecule known as methadone. And if we zoom in on that, you can see that there's, and isn't methadone given for like treating opioid addiction, heroin addiction, I think? I don't know. It's got a tertiary amine in the same molecule as a ketone. Can everybody see that structure? Yeah. And it turns out that that tertiary amine is actually quite close to the ketone. And we can actually measure the angle and the distance. So that's distance is going to show up in the lower left-hand corner here, 2.9 angstroms between atoms 1 and 2. And they noticed that the position of that atom, of that tertiary nitrogen with respect to the carbonyl oxygen made an angle of 105 degrees. And it's not showing us the line, but if you drew a line from here to here and then here to here, that angle is 105 degrees. Actually, I can make it draw a line. We can just pretend. Let's see. All right, so they noticed that fairly close contact, almost as though this nitrogen were already donating electron density into that carbon. And they found this in other structures as well. So here is the molecule protopine, I'm not sure how you say it. It's a little bit more complicated, but it also has a ketone in the same vicinity of a tertiary amine. It's a transannular interaction, but that nitrogen is constrained to be close to that carbonyl. If we do the, I'm going to make sure we draw the line so you can see it. If you make measurements here, they are in this case 2.6 angstroms apart. That's, I think, almost within van der Waals distance. If we did space filling, these would be touching each other. And if you measure the angle here, it's 102 degrees. And an interesting other feature is if you zoom in on that carbonyl, the carbons of the carbonyl, I won't highlight the sp2 hybridized carbon. What do you notice about that carbonyl?
Is it not perfectly flat?
Yeah, totally. It's not perfectly flat. And we can actually assess that by measuring bond angles there. That's less, well, that one's about 120. Let's look at this one. Also a little bit more than 120. Let's look at this one, 117. So there's some deviation from planarity. We could calculate, this kind of thing is called pyramidalization, and we could calculate sort of how bent or inverted that carbonyl is. Almost as though there's a partial bonding interaction going on here. I ran a Gaussian calculation on the methadone molecule to calculate molecular orbitals, and I'm going to see if we can see some of them. I used a natural bonding orbital analysis that can give us a sense for lone pairs and pi stars and so on. I'm going to try to capture as many of these as we can, and we'll try to show you sort of what's going on with the orbitals. Hopefully that's enough of them. I'm going to tell them to show them to us. Medium, okay, and that's going to tick away for a while. But the hypothesis here is that the reason the nucleophile is at this position is because that's where the pi star is. If you remember what we learned from, our MO chapters, more of the pi star is on the carbonyl carbon than is on the carbonyl oxygen. And that pi star is angled back away from the space between the two nuclei. So if we were to draw the pi star, I'm sort of trying to do that with my arrow here, it would be directed right along this line between carbonyl carbon and the nitrogen. Okay, and that angle of 105-ish degrees, almost a tetrahedral kind of angle, is now called the Bürgi-Dunitz angle, and additions to carbonyls generally proceed, and computational studies verify this, proceed via this trajectory. The nucleophile approaches along this Bürgi-Dunitz angle or trajectory. I'm going to see whether I clicked cancel instead of OK, so we're not going to see the orbitals today. I'll see what I can do and maybe upload them in the notes. Any questions you want to ask about the Bürgi-Dunitz angle?
Yes, we can say that this relation is really close to hydrogen bonding, like something like that.
Is it close to or exactly like, oops, because the shared window is closed. I got to share my screen again, sorry. Is it like hydrogen bonding? I suppose only the thing that the nucleophile is interacting with is not a hydrogen, but it's an empty orbital in the same molecule. So this is an interaction between nitrogen lone pairs and pi star.
So my question is because hydrogen bonding is create stability in the molecular, and sometimes this create the structure of the molecular. So in this case, happen the same. So this kind of relation affect the structure that you have in the molecular?
Yes. Can this interaction affect molecular structure and shape? Absolutely. And so unfortunately for getting through chapter 10, you've just sort of made me go off on a interesting tangent. Do you remember the N to pi star interaction we talked about in exam 2?
Yes.
With prolines? So I'm going to bring up one of these. I've actually been doing some calculations on some of these computations. Pro. Sorry, just a minute. I'm trying to bring up a. There we go. Cannot find file. Sorry. Should be here. I'm sorry, I should have prepared this, but this is what happens. Cis, trans, that'll work. So here is a model proline type compound, and you have an ester bond here. This is the carbonyl carbon, alpha carbon, and nitrogen. Can everybody see that on my screen? And then the nitrogen of proline is acetylated and is itself involved in an amide bond. And here's the carbonyl of that amide. And it turns out that the distance between those two is a little bit longer than we saw in methadone or protopine, but it's reasonably close. And the angle here to here to here is pretty close to the Berge-Dunitz angle. It's not exactly 105, it's more like 100. But Ron Rains has demonstrated that this interaction is strong enough to bias the conformation of this amide to being on the oxygen being on this side instead of the other side. And they've done orbital calculations to show that a lone pair on this carbonyl oxygen is overlapping with the pi star of this ester. And because the distance is farther, you don't see quite as much pyramidalization of this carbon. It looks, this sp2 hybridized carbon still looks pretty flat. But if you do the math, you can actually demonstrate that it's not perfectly flat. And so this is, he noticed this in proline, and then actually has noticed it in lots of alpha helices as well. So I'm going to show you an alpha helical structure. Open recent. Sorry. So I'm opening up trying to open up a pi mole image of a helix bundle. And we can zoom in on that. I'm going to hide everything. I'm going to show lines. Actually, I want to show sticks. So this is at alpha helix, and normally people have focused on it being stabilized by a hydrogen bond between this an amide nitrogen and a carbonyl carbon. However, it turns out that in addition to that, that carbonyl carbon here is pretty close to the I-1 carbonyl carbon. Oh, sorry, that's not the distance we wanted. We wanted this carbonyl oxygen is pretty close to that carbonyl carbon. It's about 3.8 angstroms away. But if you measure the angle that's formed here to here to here, I've got the wrong one, I think. Sorry. Yeah, I'm sorry, I had the wrong carbonyls. So the I+1 carbonyl oxygen is hovering over the I position carbonyl oxygen with exactly the Berge-Dunitz angle. And that distance is 2.9 angstroms. So Rains has done a bunch of structural analysis to show that this kind of thing this donor-acceptor interaction involving carbonyls actually takes place in basically all protein structures and is likely important. But I think one of the things that led him to hypothesize this was the Berge-Dunitz angle, because that angle is associated with approach of a nucleophile to a carbonyl.
So Josh, do they only ever measure Berge-Dunitz angles when the nucleophile is attached to the carbonyl? Because you wouldn't really would you be able to measure it in a free floating nucleophile, like what angle it's coming in
so
at?
I believe if you were going to do that, you would need to do computations to show the approach of a nucleophile to a carbonyl compound, to show what the transition state is, and then what the product is. Michael, you'd be more familiar with how to do that than I am, but yes, if you do those calculations, you do see approach along that sort of trajectory.
So essentially, when they found that angle, they didn't define it obviously as an end of pistar. They defined it as the angle in which the nucleophile comes in to attack the carbonyl because it's attacking the pistar.
Yes, I actually don't know what they called it when they saw it. At first, I think that was just, oh, this is interesting. This is an observation we make in crystal structures. And then after that, it became more of a, well, I wonder if that explains how nucleophiles attack carbonyl compounds. All right. So that was kind of a large digression, but it's an interesting story, and it's something you're going to hear people talk a lot about with carbonyl chemistry. So one of the things we can talk about that's pretty important is diastereoselectivity of carbonyl additions. And I realize that we've got less than 20 minutes left, but that's fine. The question is, if we have a stereocenter alpha to the carbonyl, all of a sudden the two faces of the carbonyl are no longer enantiotopic, they are diastereotopic. So here's an example. Here's this aldehyde with an alpha stereocenter. And now the two faces of the carbonyl are not the same. And so you would expect there to be some selectivity, some favoring of one side versus the other. And the question is, can we predict that? And there's three sort of main models that all lead to similar conclusions that are used to try to predict this. I'm going to focus on, I think, two of them. So the first is called the Karabatsos model. This is very similar to an earlier model called the Cram model, named after chemist Donald Cram, who's a Nobel laureate and a prominent supramolecular, used to be a prominent supramolecular chemist. What you do is you position your Sith eyes here and you look down the carbon-carbon bond, and we're going to draw a Newman projection. Here's the carbonyl carbon, here's your aldehyde proton. And then in the back, you've got this sp3 hybridized carbon with 4 different things on it. And in the Karabatsos model, you sort of rank the substituents, if you can, as small, medium, and large. Okay? If you don't know what TBDMS is, it's tert-butyl dimethyl silyl ether, so that's pretty big. And in the Karabatsos model, you rotate the bond between carbonyl carbon and alpha carbon such that the medium group is eclipsed with the carbonyl oxygen, and the large group is, so our medium group here would be the methyl. The large group would be gauche to the carbonyl or to the aldehyde proton. And then the small group would be over here. And then you ask yourself which face is less hindered, and it becomes immediately obvious you've got a blocked face and a more open face. And in particular, you ask, if I approach this carbonyl along the Berge-Dunitz trajectory with my nucleophile, which approach is going to experience less steric hindrance? And that would be from the side that has the smaller substituent aligned. If you do that and then take the product to the associated conclusion, you can get the predicted major diastereomer from carbonyl addition. And if we were to now draw our same molecule again on its side, let's see, get this right. It would be nucleophile here with OH up, I believe. I think. Get that? Did I get the stereochemistry wrong? I think I got it. Yeah, you know what, guys? I actually drew the wrong enantiomer down here. So how are we going to fix that? Sorry. I think that's all right there. Okay. So that's one way you can predict diastereo selective addition to carbonyls. What else? You want to say more about that? Any questions? So there's another model that's a bit more sophisticated, and that's called the falconon model, named after the people who came up with it. And this one's a little tricky because it involves orbital interactions. So in the falconon model, you place the large group anti to the incoming nucleophile. So as an example, suppose our carbonyl looks like this. Here is your nucleophile coming in. And at the same time, you're going to be breaking a pi bond. You want that alpha carbon in the back to be rotated such that the large group is opposite the incoming nucleophile. And you want to contrast two different possibilities. So let's say that our stereo center in the back has that configuration. And we have to ask ourselves whether it is better for which transition state seems to be more stable. Is it better for the nucleophile to approach in that direction, or is it better for the nucleophile to approach from the other side, where if you put the large group here, then medium is here and small is there? Okay. And once you put that large group sort of opposite to where the nucleophile is coming in, then your choice becomes very clear, because you know that the nucleophile approaches along the Berge-Dunitz trajectory. And so it's going to do so via the pathway that is least hindered and therefore lower in energy. Now, why would you want the large group anti to the incoming nucleophile? That's actually kind of fun. But to talk about this, we're going to have to define some terms. We're going to have to talk about a so-called nascent sigma star. Nascent means in the process of being born. If you speak Spanish, it sounds like nacimiento, which is birth, right? Or same Latin root as nativity, right? Or Navidad. Nascent means a sigma star that's being born as the nucleophile is attacking. So, sorry, dang it. Where'd my circle go? Okay. As your nucleophile attacks, dumps its electron density into the pi star, and the pi star breaks, you should be in the transition state starting to form a nascent sigma bonding orbital, and then associated with that, you should be starting to form a nascent sigma star anti-bonding orbital. And if we draw what that nascent sigma star should look like, depending on what our nucleophile is, it's going to look something like that. Now that's a cruddy drawing. Maybe I will fill in some phases to make it clearer what we're talking about. But this arrangement of the large group anti to the incoming nucleophile allows the large group, the bond between alpha carbon and large group, to donate electron density into that nascent sigma star. So it sets up a favorable donor-acceptor interaction on that side. In addition, it sets up another favorable donor-acceptor interaction on the other side because the newly forming sigma bond can donate into the carbon large group sigma star. And just to show you that that can occur as well, I'm going to redraw all of this, only we're going to get rid of our sigma star, and instead I'm going to sort of draw the cruddy orbital overlap for the new sigma bond that's forming, right? Oops. Yowza, what have I done? Here's the region where the new sigma bond is forming. And then if we were to draw the carbon large group sigma star, and it would depend on what this large group is, it would look something like that. And so you can get overlap between the carbon leaving group sigma star from the alpha carbon and the nascent sigma bond of the nucleophile. So if you happen to have on your alpha carbon, if you happen to have a group that has a lower lying sigma star, then you should put that group anti to the incoming nucleophile, even if it's not the biggest. All right, that was kind of a lot. Any questions about that falconon model for diastereoselectivity? Okay, so we're sort of drawing transition states, which makes this kind of difficult. as the nucleophile approaches the carbonyl, we're going to start to form a new sigma bond here. We're going to break this pi bond, and as we form a new sigma bond, we're going to get a sigma bonding orbital and a sigma star anti-bonding orbital. So if the large group is opposite to the nucleophile, that allows the anti-bonding orbital in the newly forming sigma star to overlap with the filled bonding orbital with the large group in the back that I didn't draw. Okay, so you've got the filled alpha carbon to large group sigma bond, and that can overlap and donate into the nascent sigma star. So sigma from the alpha carbon to the large group donating into the nascent carbon nucleophile sigma star. Similarly, in the lower left, you have donation of a newly forming sigma bond between the carbon and the nucleophile to the sigma star between of the bond between the alpha carbon and the large group. So your question was, where is the pi bond? That's breaking in this transition state as we're dumping electron density into the pi star. The pi star becomes this new pi bond. The pi and the pi star become the new pi bond and the sigma star. I'm sorry, hold on. The combination of lone pair on the nucleophile and pi star generate our new carbon-carbon bond and our new sigma star. All right. What else? So, go ahead. Right, so you're looking at the immediate vicinity, the immediate things, sterics of the immediate things bonded to the alpha carbon. So not necessarily stuff that's out downstream, but just the immediate atoms that are bonded to that alpha carbon. That you would worry about, yeah. So I guess in terms of those, yes, if you were thinking about sigma star energies, you would think only about those immediate atoms. If you're thinking about sterics, of course, you're going to consider that atom and what it's bonded to, right? CH3 versus oxygen bonded to silicon. The silicon bonded to oxygen should be bigger than a methyl group. If you have a particular, your text says if you have a carbon-nitrogen or a carbon-oxygen bond on the alpha carbon, that's the one you want anti to the leaving group because the sigma star there is low enough in energy to participate in this donor-acceptor interaction. All right. Well, that's page 16 of of what I've taken so far of chapter 10. I've got like almost 30 pages of notes, which we're obviously not going to get to. I think what I'm going to try to do is just show you the most important things, like I've said. We talked today about the Berge-Dunitz angle, which if you've taken a physical organic chemistry class, you ought to know about. We've talked today about the falconon model for carbonyl addition diastereoselectivity. Next time, we're going to talk about Baldwin's rules, which are sort of back of the envelope rule of thumb for predicting whether certain kinds of cyclizations are going to be favorable or not. We're going to see that that's related to the Berge-Dunitz angle. So it applies in a lot of different situations. Anyway, Until then, good luck on your exam. If you have specific questions, feel free to stop by and ask me or email me. But if not, make sure you send me what you've got by the end of the day, and I'll get them graded and back to you soon. And with that, we will go ahead and end our class.